Hello everyone. Welcome to this Advanced Liquid Penetrant Testing training session. In this module, we are going to study PT from both the practical inspection side and the certification exam side. So whether you are preparing for Level 2, Level 3, or already working in the field as an inspector, this training will help you understand how PT actually works in real industry applications. Now, one very important thing. In PT, many people memorize the process steps, but they do not understand the actual inspection logic behind the method. And honestly, that becomes a major problem during certification exams, and even more during real field inspection. So throughout this session, I will explain not only what we do in PT, but also why we do it. We will discuss surface preparation, penetrant sensitivity, developer performance, lighting requirements, process control, common inspection mistakes, and important exam-focused concepts. This training is designed to feel like a real classroom session conducted by an experienced Level 3 instructor. So relax, focus carefully, and let's begin our advanced PT training. Now, before we go deeper into the PT process, let's first understand what we are going to cover in this training. First, we'll discuss the advantages and limitations of PT. This is a very important certification exam topic, especially for comparison questions between PT, MT, UT, and RT. After that, we'll move into the physical principles behind PT. Now, this section is extremely important, because if you do not understand surface tension, wetting ability, and capillary action, then you cannot truly understand how penetrant enters discontinuities. Then we'll study the complete PT processing sequence, step by step. And during that section, I'll explain where inspectors commonly make mistakes, especially during cleaning and penetrant removal. After that, we'll discuss penetrant materials, developer types, sensitivity levels, and inspection methods. Then we'll move into indication interpretation and evaluation. Now, this becomes very critical during actual inspection, because one wrong interpretation can lead to either rejecting a good part or accepting a defective part. And finally, we'll discuss process quality control. This is one of the highest scoring Level 3 topics, because a Level 3 inspector is responsible for the entire PT system performance. So throughout this session, pay very close attention to all practical notes and exam-focused concepts. Now let's start with the advantages and limitations of liquid penetrant testing. This is one of the most frequently asked theory topics in certification exams, so please pay close attention here. First, let's discuss the advantages. One major advantage of PT is complete surface coverage. No matter how complex the geometry is, PT can inspect the entire exposed surface. That is why PT is widely used for welds, castings, forgings, machined parts, and aerospace components. Another major advantage is high sensitivity. PT can detect very small and tight surface cracks that may not even be visible to the naked eye. Now, this is very important for certification exams. PT is extremely sensitive to very fine surface open discontinuities. Another important advantage: PT works on both ferrous and non-ferrous materials. Unlike magnetic particle testing, PT does not require magnetic materials. This comparison is frequently asked in Level 2 and Level 3 exams. PT is also fast, economical, and suitable for high-volume production, and indications appear directly on the surface, making visual interpretation easier. Now let's discuss the limitations, and honestly, this is where many candidates lose marks during exams. The biggest limitation of PT cannot detect subsurface discontinuities. Please remember this carefully. PT only detects defects that are open to the surface. If the crack is internal and not connected to the surface, penetrant cannot enter. And once penetrant cannot enter the discontinuity, the defect cannot be detected. This is one of the most important theory questions in PT certification exams. Another limitation: PT requires a very clean surface. Oil, grease, paint, rust, machining smear, or dirt can block penetrant entry completely. From practical field experience, poor cleaning is one of the biggest reasons for PT failure. Surface roughness also affects sensitivity. Very rough surfaces can trap excess penetrant, creating heavy background indications and false interpretation problems. PT is also not suitable for porous materials because penetrant gets trapped everywhere, making evaluation almost impossible. And finally, PT cannot determine discontinuity depth. It only tells us that the defect is open to the surface. It does not tell us how deep the crack extends internally. Now let's move into the physical principles behind liquid penetrant testing. This section is extremely important because these three principles are the actual foundation of PT. If you understand these concepts clearly, you can understand why penetrant enters discontinuities. The first principle is surface tension. Surface tension is basically the force that holds liquid molecules together. You can imagine it like a stretched elastic skin on the liquid surface. Now in PT, this becomes very important, because if the liquid molecules hold together too strongly, the penetrant will not spread properly across the test surface, and that is not what we want. For successful PT, the penetrant must spread smoothly over the surface and enter very tight discontinuities. That brings us to the second principle: wetting ability. Wetting ability means the penetrant can spread naturally across the material surface. Now this depends mainly on the contact angle. If the contact angle is less than 90 degrees, wetting is good. The penetrant spreads properly and enters the discontinuity. But if the contact angle becomes greater than 90 degrees, the penetrant starts beating up on the surface. And once that happens, penetrant entry becomes poor. Now the third principle, and probably the most important principle in PT, is capillary action. This is the actual mechanism that pulls penetrant into cracks. Capillary action is the tendency of liquid to move into small openings naturally. Cracks, pits, seams, laps, all act like tiny capillary tubes. And here's the interesting part. The smaller the discontinuity opening, the stronger the capillary effect becomes. That is why PT can detect extremely fine surface cracks. Now this complete sequence is very important for certification exams. Adhesive force must be greater than cohesive force. That creates good wetting. Good wetting creates a contact angle less than 90 degrees, and that allows capillary action to pull penetrant into the discontinuity. Now this slide explains the relationship between contact angle, wetting ability, and capillary behavior. And honestly, many candidates get confused here. So let's simplify it carefully. Look at case A first. Here the contact angle is greater than 90 degrees. That means cohesion is stronger than adhesion. In simple words, the liquid prefers sticking to itself instead of spreading across the surface. As a result, the penetrant does not enter the discontinuity properly. This condition is not suitable for PT. Now look at case B. Here the contact angle is exactly 90 degrees. This is considered a neutral condition. Cohesion and adhesion are balanced, so no capillary rise occurs. Again, penetrant entry becomes ineffective. Now finally, look at case C. This is the ideal PT condition. The contact angle is less than 90 degrees. Adhesion becomes stronger than cohesion. The penetrant spreads smoothly across the surface, and capillary rise occurs naturally. This allows penetrant to enter tight surface discontinuities effectively. Now, this next point is very important for certification exams. Only when adhesive forces are greater than cohesive forces will penetrant properly enter discontinuities. This concept is frequently asked in Level 2 and Level 3 theory exams. Now let's discuss the different PT processing methods. This is another very important certification exam topic. There are 4 major PT methods. Method A, water washable penetrant. This method contains a built-in emulsifier. That means excess penetrant can be removed directly using water spray. Now, the advantage here is speed and simplicity. That is why Method A is commonly used in high-volume production. But there is one major problem: overwashing. And from practical field experience, this is one of the most common inspection mistakes. If excessive water pressure or washing time is used, penetrant inside shallow discontinuities may also get removed. And once penetrant gets removed from the crack, sensitivity decreases significantly. Now, Method B, post-emulsifiable lipophilic. Here, a separate oil-based emulsifier is applied before water rinsing. This provides better removal control compared to Method A. But emulsification time becomes extremely critical. Too little time, surface penetrant remains. Too much time, penetrant inside the discontinuity may also be removed. This timing control is a very important exam concept. Now, Method C, solvent removable. This method is commonly used for portable inspection and field applications. No water system is required. Very useful for localized weld inspection and maintenance work. But remember, solvent removable methods are usually limited to small inspection areas, and the solvents may also be flammable. Now, Method D, post-emulsifiable hydrophilic. This is generally considered the preferred PT method. Please remember this carefully for exams. Hydrophilic methods provide better removal control, cleaner background, and higher reliability. But concentration control becomes very important, usually between 5 and 30%. And this concentration must be monitored carefully during operation. Now, one important comparison question. Method D is generally preferred over Method B because it provides better control and lower background fluorescence. Now we are looking at the complete 7-step PT process. And please remember this carefully. PT is a process-controlled inspection method. Every single step affects the final inspection quality. Now, Step 1, surface preparation. This is the most critical step in the entire PT process. This question appears very frequently in certification exams. If contamination blocks the discontinuity opening, penetrant cannot enter. And once penetrant cannot enter, the inspection becomes unreliable. Oil, paint, grease, rust, dirt, machining smear, all must be removed properly, and after grinding or machining operations, acid etching may sometimes be required to reopen smeared discontinuities. Now, Step 2, penetrant application and dwell time. The penetrant needs time to enter the discontinuity through capillary action, typically between 10 and 30 minutes. And one important rule: do not allow penetrant to dry, unless specifically permitted by procedure. Now, Step 3, excess penetrant removal. This is where many inspectors make mistakes. You must remove surface penetrant without removing penetrant trapped inside the discontinuity. That balance is extremely important. Now, Step 4, developer application. The developer acts like blotting paper, It draws penetrant back out from the discontinuity and creates contrast for visibility. A thin and uniform developer layer is very important. Too much developer can mask indications. Too little developer reduces sensitivity. Now step 5, development dwell. This allows indications to develop completely, typically between 10 and 120 minutes. Now step 6, inspection and documentation. This may be performed under white light or UVA light, depending on penetrant type. And finally, step 7, post-cleaning. Residual penetrant and developer must be removed properly to prevent contamination and corrosion problems later. Now let's discuss penetrant materials, dye types, and sensitivity levels. This is another very important exam topic. There are mainly 3 penetrant types used in PT. Type 1, fluorescent penetrant. Type 2, visible dye penetrant. And Type 3, dual mode penetrant. Now let's understand them one by one. First, Type 1 fluorescent penetrant. This method is inspected under UVA light, usually between 320 and 400 nanometers, and this method provides the highest sensitivity. This is very important for certification exams. Fluorescent penetrants can detect extremely fine discontinuities because the human eye is very sensitive to yellowish-green fluorescence under dark conditions. Now, fluorescent penetrants are available in multiple sensitivity levels, from ultra-low all the way up to ultra-high sensitivity. And this becomes very important when selecting penetrant systems for aerospace or critical inspection applications. Now, Type 2, visible dye penetrant, usually red dye under white light. This method is simpler, cheaper, and easier for general inspection, but sensitivity is much lower compared to fluorescent PT. Visible penetrants are generally limited to level 1 sensitivity only. Now Type 3, dual mode penetrant. This can be viewed under both UVA and white light. But remember, sensitivity is still lower compared to dedicated fluorescent systems. Now this next point is very important for exams. Only fluorescent penetrants provide all 5 sensitivity levels. Visible and dual mode penetrants are limited mainly to level 1 sensitivity. This comparison is frequently asked in level 2 and level 3 certification exams. Now let's move into developers. And honestly, many inspectors underestimate how important developers are in PT. The developer has 2 major functions. First, it draws penetrant back out from the discontinuity. Second, it creates a contrasting background, making indications easier to see. Now let's discuss the different developer forms. Form A, dry powder developer. This is commonly used for rough surfaces and automatic systems. It is also easier to clean after inspection. Now Form B, water-soluble developer. This developer is applied before drying, and concentration control becomes important, usually checked using a hydrometer. Now Form C, water-suspendable developer, very similar to Form B. But this type requires continuous agitation because particles can settle inside the tank. Now Forms D and E, non-aqueous developers. This is a very important certification exam topic. These developers provide the highest sensitivity for detecting fine discontinuities, usually applied by aerosol spray onto dry surfaces. Form D is generally used for fluorescent inspection. Form E is used for visible dye inspection. Now, from practical experience, improper developer application is one of the most common reasons for weak or unclear indications. Too much developer can mask indications completely. Too little developer reduces sensitivity. So always apply a thin, uniform coating. And please remember this important exam question. Which developer provides the highest sensitivity? Answer: non-aqueous developers, forms D and E. Now we come to one of the most important practical inspection areas in PT: indication, interpretation, and evaluation. And this is where real inspector skill becomes critical. The first step: observation. This simply means scanning the part surface for indications. The second step: interpretation. Now this means determining whether the indication is relevant or non-relevant. And finally, evaluation. This means comparing relevant indications against the applicable acceptance criteria. Now let's discuss relevant indications first. Continuous linear indications usually indicate cracks, laps, or seams fully open to the surface. Intermittent linear indications may indicate partially open cracks or laps. Round indications usually suggest porosity or corrosion pits. Now let's discuss non-relevant indications. This is very important for certification exams. Improper penetrant removal can create false background indications. Threads, holes, sharp radii, or complex geometry can trap penetrant and create misleading indications. Even fingerprints can create smearing patterns. And from practical field experience, many inspectors wrongly reject components without properly confirming whether the indication is truly relevant. That is why the double development technique becomes important. First, clean the indication area carefully. Then allow the solvent to evaporate completely. After that, apply a light layer of developer again. If the indication reappears, it is likely a true discontinuity. If it disappears, it was probably non-relevant. This technique is commonly discussed in Level 3 practical examinations. Now let's discuss acceptance and rejection criteria. And please remember this carefully. Actual acceptance limits always depend on applicable codes, standards, customer specifications, and approved written procedures. ASME, AWS, AMS, and customer requirements may all have different criteria. Now in this example, linear indications greater than 0.25 inches are considered rejectable. This is a very common theory question. Location is also extremely important. Even a small indication may become rejectable if it appears inside a critical weld region or high-stress area. Grouping is another important factor. Several small indications close together may indicate a serious discontinuity cluster, and total indication quantity is also controlled. Now, one important thing for Level 3 candidates: do not memorize acceptance criteria blindly. You must always verify the applicable code, the procedure, and the governing specification. Because Level 3 inspectors are responsible for correct code interpretation. This is frequently asked in Level 3 certification exams. Now we arrive at one of the highest scoring Level 3 topics: process quality control. Please pay very close attention here. The primary cause of PT system failure is contamination. This is extremely important. Water, oil, paint, cleaners, dust, or chemical contamination can seriously affect penetrant performance. Now let's look at penetrant testing controls. The penetrant should spread smoothly across the surface. If the penetrant starts beating up, contamination may exist. Fluorescent penetrant brightness can also be checked by comparing reference samples with in-use samples. Water contamination may also be checked using separation methods inside glass tubes. Now removers must also be monitored carefully. Using UVA light, inspectors can verify whether penetrant contamination exists inside the remover system. Developer systems also require concentration checks and contamination monitoring. Now, equipment controls are equally important. Dryer temperature, fan performance, and system cleanliness all affect PT quality. Inspection booths must also maintain proper lighting conditions. And this next point is very important for exams. Ambient white light for fluorescent inspection must be less than or equal to 2 foot candles. UVA intensity must be at least 1,000 microwatts per square centimeter. These values are frequently asked in certification exams. Finally, complete PT system performance is verified using cracked chrome panels, starburst panels, or penetrant system monitors. These verify the performance of the entire PT system. Now let's discuss inspection conditions and lighting requirements. This is one of the most important PT theory areas. For fluorescent inspection, ambient white light must be controlled carefully. Field inspection areas should not exceed 2 foot candles. Inspection booths are even stricter, typically around 0.2 foot candles. Now, UVA intensity must be at least 1,000 microwatts per square centimeter at the inspection surface. And the UVA wavelength should be between 320 and 400 nanometers. Dark adaptation is also important. Inspectors should remain in dark conditions for at least 5 minutes before inspection. This improves eye sensitivity significantly. Now, visible dye inspection is different. Minimum white light intensity should be 100 foot candles or 1,000 lux, and dark adaptation is not required. Indications usually appear as red marks against a white developer background. Now, from practical field experience, poor lighting control is one of the biggest reasons for missed indications. Even a high-quality penetrant system becomes unreliable if lighting conditions are incorrect. So lighting verification must always be performed before inspection. Now let's quickly review the most important points from this training. PT detects surface open discontinuities only. It cannot detect subsurface defects. The 3 physical principles behind PT are surface tension, wetting ability, and capillary action. Surface preparation is the most critical process step. If contamination blocks penetrant entry, the entire inspection becomes unreliable. Fluorescent penetrants provide much higher sensitivity compared to visible dye systems. Hydrophilic method D generally provides better removal control than lipophilic method B. Non-aqueous developers provide the highest detection sensitivity. And finally, contamination is the primary reason PT systems fail. These are some of the most important concepts for both certification exams and practical inspection work. Now let's quickly review some important certification-style questions. Question 1. Which limitation is unique to PT? Answer: PT cannot detect subsurface discontinuities. Question 2. Why must adhesive force be greater than cohesive force? Because this creates good wetting, a contact angle less than 90 degrees, and proper capillary action. Question 3. What is the most critical PT process step? Answer: surface preparation, because contamination prevents penetrant entry. Question 4. Why are fluorescent penetrants more sensitive than visible dye penetrants? Because the human eye detects yellowish-green fluorescence very efficiently under dark conditions. Question 5. What is the primary reason for PT system failure? Answer: contamination. And finally, which developer provides the highest sensitivity? Answer: non-aqueous developer, forms D and E. Now, if you can explain these questions confidently in your own words, then you are developing true Level 3 understanding. Thank you, everyone, for attending this advanced liquid penetrant testing training session. I hope this session helped you understand not only the PT process itself, but also the practical inspection logic behind every requirement. Please continue reviewing the important topics we discussed today, especially surface preparation, capillary action, penetrant sensitivity, developer selection, lighting requirements, and process quality control. These are extremely important from both the practical inspection side and the certification exam side. And always remember, a great inspector does not simply follow procedures mechanically. A great inspector understands why each requirement exists. Thank you once again, and I'll see you in the next advanced NDT training session.